This is lesson 3 for Essential Math Grade 12s in the probability unit. And today we're going to talk about odds. You know what we're going to do? We're going to go back to the first page really quickly. We're going to go back to this Calvin cartoon. I wonder what it must be like if your parents ask you, hey, what did you do in class? It's like, I don't know. We've been talking about this Calvin cartoon for a week. I don't know what's going on. But anyway, remember when I first made you read this cartoon and somebody in the class, I think the first person when I asked, what do you think Calvin should expect to get on this test? Somebody said 50-50. And that's a perfectly good way of thinking about it. But you know what? That's not really a probability. As soon as you compare two numbers like that, and it's the same number especially, you're not in the world of probability. You're in the adjacent universe that we call odds. So lesson 3 is all about the difference between probability and odds. Here's what probability is, right? Probability is desired over possible. It's got this nice little formula. Probability that an event happens is the number of ways that I want to have it happen. So desired outcomes over all the ways that the event could actually turn out. So for example, what's the chance that I roll a die and get a 6? Well, it'd be 1 out of 6. What about, what's the probability of, you don't have to write this down, what's the probability of rolling that die and getting an even number? Ooh, how many do I desire now? The even numbers would be the 2, the 4, and the 6. So 3 out of 6, which is a half. Okay? So that's probability. That's not the same thing as odds. Another way to think about probability is in terms of the odds against an event occurring or odds in favor of event occurring. So the two blanks that we want first are against and favor. Odds is a ratio that compares the number of possible favorable outcomes to the number of possible unfavorable outcomes. Favorable to unfavorable. You can express it like a fraction. I'm going to put down here most people don't. I'd actually prefer it if maybe we just leave fractions, decimals, and percents for the probability questions. Anytime we're doing an odds question, we'll look at our answers and know right away that it's an odds because we'll stick to a side-to-side ratio. And it's going to be what we call a part-to-part ratio. I'm going to just break free from the notes for a second to explain what I mean by part-to-part ratio. I'll show you what I mean. Remember the first time you encountered fractions back in elementary school? You probably got a picture like this. And then maybe this was shaded, this was shaded, this was shaded. And then we asked you, what fraction is not shaded? And you probably would go, oh, well, that's the fraction you were probably supposed to say. But you know, if I asked you what ratio it is, well, now it's kind of, what do you mean by ratio? You could say 1 is shaded out of 4 in total, not if I said it was a part to whole ratio. What's the ratio of shaded to pieces? 1 to 4. Oh, sorry. No, yeah, it's total. 1 to 4. Oh, sorry, not shaded. I meant to say not shaded. Not shaded. Thank you. Sorry. Now it is. Yeah, you're right. It was wrong. Now it's right. How many are not shaded? 1 out of 4. What's the ratio for that? Well, you could say it's 1 to 4. 1 not shaded to 4 pieces in total. Part to whole. But chances are you probably didn't talk ratios that way. Most of the time when we use ratios with the 2 dots like that, we do part to part. And we would have said, oh, this thing is 1 to 3. 1 not shaded to 3 shaded. That's more the way we think about ratios. We don't usually put the whole thing on one side. So that automatically makes it a little different than the probability formula. Because notice the probability formula, the bottom number is always total, not part. So when I look at rolling a die, so let's go back to rolling a die. What's the probability of rolling a 2? Well, we're going to assume it's a 6-sided standard die, 1 out of 6. Unless it's that die I showed you the other day that has 3 2s on it. What's the odds in favor of rolling a 2? Odds in favor means how many ways favorable versus how many ways are unfavorable. And this is, again, this is the odds in favor, also called odds for. What are the odds for this event happening? Well, it's 1 to 5. Why is it 5 instead of 6? Because 5 things on the die aren't a 2. I don't worry about the total. I worry about how many things aren't what I want to have happen. Both of these things should add up to that number, always. That's how odds work. What are the odds against rolling a 2? Well, the odds against rolling would be, so this is again odds against. How many things are not a 2? 5 to 1. And there we go. That's how odds works. And we didn't do this the other day, so we're going to do this today. Tree diagram. This is kind of a review of some grade 7-ish, grade 8, no, grade 8. Grade 8's when you do this probability. Grade 8 stuff, tree diagram. Type of organizer for displaying outcomes of an event. Each branch represents a different possible outcome. A coin is tossed 3 times. Use a tree diagram to represent the different scenarios. Okay. First coin could be heads or tails. Second coin, that'll be this row. They call it a tree diagram because it's like it grows branches. And you saw me do this the other day. This is actually, isn't this the same example I used the other day? Yeah, it is. Okay, so this is easy. We can go fast. Third coin. Hang on, let me make that go away. There we go. Third coin. If I threw heads for the first coin, heads for the second coin, the third coin could be heads or tails. I threw heads on the first coin, tails on the second coin. The third coin could be heads or tails. The first coin could have been tails. The second coin could have been heads. Then I could get heads or tails on the third coin. And again, the first coin could have been tails. The second coin could have been tails. Then I could have got heads and tails. Okay. Now, determine the probability of all 3 tosses landing heads. So how many, what's the formula for probability again? Probability is desired over possible. You could say total too if you like. So the probability of heads, heads, heads is what? Well, there is 1, 2, 3, 4, 5, 6, 7, 8 possible things that can happen. One of them is heads, heads, heads. All the others are different. So my final answer is 1 out of 8. What is the odds in favor of 3 tosses all landing heads? One of the ways had all heads, 1, and then 1, 2, 3, 4, 5, 6, 7 of the outcomes was not all heads. What are the odds against all 3 tosses landing on heads? This is an easy question. You just reverse those two. 7 to 1. So notice probability is related, but it's written and expressed kind of differently. It's a slightly different way to think about it. Okay. Next question. A 6-sided die is rolled. Determine each of the following. The probability of rolling a number less than 3. Okay, what is the probability of rolling a number less than 3? So let's see, what is that going to be? The numbers less than 3 are 1 and 2. So my probability of rolling a number less than 3, everybody okay with that symbol being less than? Probability of a number less than 3 is 2 out of 6. And if I leave it like that, I lose half a mark. What can you do with 2 over 6? Nah, I'm not rounding it. Simplifying it to 1 out of 3. Now, what are the odds in favor of a number less than 3? Well, there is 2 numbers on the die that are less than 3, what I want, my favorable, but there's 4 that aren't. And just like fractions, what can I do with 2 to 4? I can simplify that to 1 to 2, because just like both of these numbers divide by 2 nicely, both of these numbers divide by 2 nicely. So just like fractions, when you're doing odds, if you can simplify it, you have to, or it's going to cost you half a mark. That was your question, right? Yeah. Odds against, well, for odds against, I just have to, again, flip it. But if I wanted to think it through, okay, how many things are not less than 3? Well, 3 is not less than itself. So there's 3, 4, 5, 6. So that's 4 things. How many things are less than 3? 1 and 2, 2 things. The odds are 2 to 1. 2 to 1 odds against rolling a number less than 3. Okay, given that the odds in favor of an event occurring is 5 to 2, what's the probability that the event occurs? I haven't done this in a long time. I'm going to use my red pen, and I'm going to make a mistake on purpose. Don't write this down. I'm writing in red. Oh, it's 5 over 2. Now, how do you know right away that's a ridiculous answer for a probability? The number is higher than what? What's the limit for probability? Look back to the first page of the booklet. What's the biggest that probability can be? I'll give you a hint. Let's make a percent out of that. That would be 2.5, which is 250%. I dare you to find me the event that has a 250% chance of happening. That does not make sense. That's not how it works. So, how does it really work? Well, remember that this ratio of 5 to 2 is in favor and not in favor. So that means the total possible events is what? There's 7 things that can happen. Therefore, a 5 to 2 odds is equal to a 5 out of 7 probability. Does the logic of that make sense to you when you think it through? That's how probability and odds relate to each other. So they're pretty similar. You can always get one from the other. But they're expressed differently, and you got to think about them a little bit differently. Okay, just like the last 2 lessons, I'm going to end with a little grade 8 review. So we reviewed tree diagrams. You know what? I did this one with the other class, but I forgot to talk about it with you guys. So it might be on yesterday's video. So if there's people following along with videos, this one might have been on yesterday's video. But I'm going to go back to Calvin one more time. Good old Calvin. And here's a conversation we had yesterday with the morning class, or with the afternoon class that I forgot to have with you guys. So if we're Calvin here, we said we expect, come on, eraser. For some reason this won't erase. I don't know why. Oh, there we go. If we're Calvin here, we expect to get 50% correct. and 50% wrong. What if I had 4 Kelvins and I did this experiment? I said, because remember, yesterday we did experimental probability, right? So I said, okay, 4 guys, 4 students, don't even read the questions on the true-false test. Just take your coin, flip it for every question. T for tails, make that a true. When you get a heads, make that a false. I would expect all 4 of them to get around 50%, but that might not be what happens. Maybe the first student got 9 out of 10. Maybe the second student got 8 out of 10. Maybe the third student got 7 out of 10. And the fourth student got 6 out of 10. And I average those together. That's 8.5. No, it's not. Let's try that again. That's 7.5 out of 10. That's 75%. Now, does that mean what I just did was wrong? Nope. That's experimental probability. It's not the same thing as theoretical probability. The theoretical probability is that this average should have been 50%, because that's what Kelvin would get. That's what 4 Kelvins would get. All right, now what if I had 1,000 Kelvins? What if I took every kid in this school, that's almost 1,400, and had them do this 10-question true-false test? What do you think would happen to these fractions now? Well, there might be a couple kids who got 1 out of 10. But overall, when I average together thousands instead of 4, what do you expect to happen? Even out's a good way. So the person who just answered my question said, it'll even out. What do you mean by it'll even out? It will get closer and closer to 50%. There is a name for this. And this is what I forgot. This was supposed to be part of yesterday's lesson. It's called the law of large numbers. And the law of large numbers says experimental probability excuse me, will always get closer to equaling theoretical probability as the number of trials gets larger. I mean, right now, I had 4 Kelvins tried. I got 7.5 out of 10. One more. Say I added one more Kelvin to the mix, who got 5 out of 10, which is kind of what you'd expect. Well, suddenly this now becomes 7 point something. It might even be 6 point something. I'd have to, let's do the math. 17, 24, 30, 35, 35 out, no, that's not right. 17, 24, 30, 35. Oh, yeah, I guess it is. 35 over 10. Yeah, the average mark here is, no, the average is 35, no, 17, 24, 30, 35, right? So 11, 18, 11, 18, 26, 35. So they add those up, you get 35. 35 divided by 4 is 8. Oh, it's still over 8 now. It's over 8? Oh, yeah, I guess it is over 8. So that would be 8. Oh, that's 5. That's what I'm doing wrong. 35. It's exactly 7 now, which makes sense because that's the middle number. Yeah. So that's 7 out of 10. So now it's down to 70%. Suppose I had a couple more kids who wrote, and one of them's high again, 6 out of 10, but then I had a 2 out of 10. Somebody very unlucky on guessing multiple choice with a coin. And then a 3 out of 10. As I keep going, doing trial after trial after trial, this number will just keep on approaching 50%. Will it ever exactly equal 50%? Oh, it might not, but it'll get closer and closer and closer forever. That's the law of large numbers. Sometimes it's also called regression to the mean. This is in sports a lot. Very often you'll see something like a goaltender win a whole bunch of games in a row. And it's like, well, better give them millions of dollars for contract because they're the best goalie ever. Well, look at their past performance, at what their average performance is, and guess what? Given enough time, they will regress to their mean. They will probably go back to being kind of the goalie they were before. They're just on a hot streak right now. Those kinds of things happen all the time. It's called the law of large numbers when you're counting. Sometimes, again, regression to the mean. So that was something I wanted to talk about yesterday, and I forgot to. The other thing I was going to do today was a quick reminder on how to calculate independent events. And again, you did this in grade 8. Independent events works like this. If A and B are independent of each other, and that means event A will not influence event B, then the probability that A and B both happen is equal to probability of A times the probability of B. So it's a nice little formula. So for example, here's an example. I'll slow down a little bit for you. Give you a sec to catch up. Okay, let's do some examples. What's the probability that I roll a die and get a 6, then I flip a coin and I get heads? Okay, think about this. The probability that I roll the 6 is 1 out of 6. The probability that I get heads is 1 out of 2. And if you don't remember how to multiply fractions, it's just top times top, bottom times bottom. That looks like too small a number. Let's check it with a tree diagram. My die could be, or let's do the coin first. My coin could be heads or tails. And then after flipping the heads, I could get a 1 on the die, or a 2, or a 3, or a 4, or a 5, or a 6. After flipping the tails, I could get the die a 1, a 2, a 3, a 4, a 5, or a 6. There is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 outcomes. One of them is a heads and a 6. It works. Multiplying fractions saves you having to make a tree diagram. All right, let's try a different one. Let's talk cards. What's the probability that I take my deck of cards here? This is really exciting for the people watching this on video. I am shuffling a deck of cards. First, I'm taking the jokers out. Now I am shuffling a deck of cards. There we go. You can hear that. Hold that up to the microphone so people can hear it. Oh, my tendonitis is getting me here. There we go. That's better. Okay. What is the probability that I deal you an ace, shuffle it back into the deck, and deal you another ace? So what is the probability of an ace and an ace? Okay, how many aces are in the deck again? 4. 4 out of 52. I put it back, I shuffle, shuffle, shuffle. The second event has nothing to do with the first. So 4 out of 52 again. Now you might be looking going, ooh, those numbers are going to be big. Well, I can fix that. Simplify before you multiply. Ooh, that rhymed. I like that. Simplify before you multiply. And don't forget 1 times 1 is not 2. And there's actually, that's pretty low. 1 out of 169. Okay, now I'm going to say this is, of course, I'm going to say that was with replacement. Do you get what I mean by that? Because I put the first card back before I gave you the second one. What is the probability of ace and ace without replacement? So this is more like a real game of cards, where I give you a card, you keep it, and then I give you a next card. Placement. There we go. So let's think about that. So let's shuffle. So what is the probability? Watching me shuffle. What's the probability that I just gave Nick an ace? Well, we already know that's 1 out of 13. I mean, yeah, technically it was 4 out of 52. But wait a minute. He's not giving that back. What's the chance that the next one's an ace? Any idea? Think about it. Is there 4 aces left after the first one's been pulled out? No. It's 3 out of 51. Very good. And by the way, that simplifies too, so that the numbers stay small. That's actually 1 out of 17. 3 times 17 is 51. So that's a different number. I don't remember what 13 times 17 is. 220 something? 13. I don't know my 13 times table, oddly. 221. Notice it's actually harder, which makes sense. There's less aces to choose from for that second card. So yeah, if I deal you 2 cards, you would expect me to deal you a pair of aces 1 out of every 22 times. Ooh, let's change that to odds. 1 to 220 in favor. Or most of the time people say the odds against me dealing you a pair of aces is 220 to 1. Not very good odds. So there we go. That's a quick little refresher on how you're supposed to do independent events. You're supposed to remember that from grade 8 because it doesn't really, they assume you understand that and know that for this curriculum. All right, I'll stop my video there. But okay, Nick, how'd I do? Was it 2 aces?
It was an ace. There was an ace in you. Ace of hearts.
I missed it by a card. Oh, no, I didn't. I really blew it. I missed it by 4 cards. So I don't know if you know this or not, but there's a reason why you are supposed to, when you're playing cards with somebody that you might not trust totally, look at this person. If she's dealing the cards, she shuffles, then she puts it down for me. And then what am I supposed to do before we actually deal the cards? You're supposed to cut the deck. Because a person with some skill can, my dad was masterful at this. I'm terrible. Now I have 10 and I guess I don't think it's good. It looks like I'm just shuffling, but what I'm actually doing is I'm looking for cards. Like, I don't know, I just stopped pulling the cards at that ace, and then of course I do this. And now where's that ace? It's at the bottom of the deck, and it looks like I'm shuffling, but look carefully at my hand here. I'm always pulling that ace this way, and kind of getting it out of the way while I shuffle the rest of the cards. So that ace is there, right? And then I have one of 2 things I can do. This one's obvious and easy to catch. I could do one more shuffle like this, where I just put the ace second in line. There we go. I just dealt 2 aces if this was me playing you, right? Because I had an ace on the top and then the other person with an ace on the back. But that's easy to catch. Harder to catch for the people who are good at it. Again, my dad used to do this. I've never been good. Is just leave the aces at the bottom, and then as you're dealing the cards, it looks like you're pulling out the card with your finger like that, but you actually do it quickly and pull it like that. So it's called dealing from the bottom of the deck. So if she was to actually have the deck all stacked and ready to go with all the aces she wants on the bottom, and then she puts it down in front of me and I do that, well, that foiled it fine, right? It doesn't matter what the bottom of the deck was, it's somewhere in the middle. And there's no chance that she'll get it for sure in a game where you don't control how many cards somebody gets. There are people who can shuffle cards so professionally that you can give them a brand new deck. Did you know this? That a brand new deck is actually in order? Starting from the ace of spades all the way to the king of diamonds. Go through ace, 2, 3, 4 in the spades, and then ace, 2, 3, 4 in the clubs, then ace, 2, 3, 4 in the hearts, then ace, 2, 3, 4 all the way to the king of the diamonds. It's always in order when you buy the deck. There are guys who can shuffle perfectly. In other words, they can do what I just did and know that they went 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, so that they know exactly where every card is. And you give them 13 shuffles and they'll get the deck back to the original order that it was. And you can't look at them and see that they're doing it. Because they're just, it's like magicians with sleight of hand. There's a reason why most magicians learn how to do card tricks. Right? So, just like those phony dice I was warning you about, weighted dice, never play cards for money, ever. There's always somebody out there that's going to figure out a way to try to cheat you. Can't believe I missed that second ace. Oh, I'm going to blame my tendonitis. All right, what are we doing now? You can work. I'm going to move things around here. I said on the blog, what did I say on the blog? I said on the blog that we'd go over lesson worksheet 1, but I could see that some people barely started it. So I'm going to let tomorrow be a work period. So I'm going to say, we went through lessons 3, which focuses on the difference between probability and odds. then I'm going to say, okay, then we had time to work on finishing worksheet 5A and starting worksheet, oops, I can't spell worksheet. Oh, is that right? Is worksheet 5B after the lesson I just did? Again, I'm not used to this booklet. It's different than the booklet I used last year. Yep, 5B. Worksheet 5B. In the probability workbook, we will correct them on Monday. So I will let you have tomorrow too as a work period for worksheet 5B. And if anybody finishes them both, I actually have some really good challenge problems you can try. And I'll work at getting answer keys up on here too. So tomorrow I'll post answer keys. So there we go. All right, let me get my video done here. Oh, I'm still recording? What?